Today we consider our second iterative method to go alongside Jacobi method, and it's called the Gauss-Seidel method. And it turns out that it's actually best viewed as a modification of Jacobi to try and make it a bit faster. So I'll explain how we can formulate the Gauss-Seidel to make it a bit faster than Jacobi. And then we'll start on our sort of journey into analysing iterative methods of matrices and matrix inversions, namely using what's called the L plus U plus D decomposition. Okay, so last time we looked at the Jacobi method and how when you start with an A matrix like this, AX equals B, you can rewrite it as X equals C minus B times X. So we define a B matrix, do this by simultaneous equations method, and we have a C vector. And we started off X at 0, 0, 0, arbitrary point, and just iterated this multiplication. And once I managed, out popped something very close to the true solution. At the end of the day, the error was of order 10 to the minus 5. So that's the Jacobi, the first encounter with the Jacobi method. Today I just want to also introduce the other method that we're going to be considering, which is the Gauss-Seidel method. So you may notice that sometimes we introduce methods in pairs, one that's better than the other, so that illustrates, allows us to illustrate our methodologies for convergence, say in this case. So that's the reason we're doing this, is we're using two methods. One was Jacobi, and then this Gauss-Seidel, which really is a modification to Gauss-Seidel method. Sorry, it's the Jacobi method rather, to accelerate its form. So if we write out Jacobi, we say line by line. So that was, it was x n plus 1 equals c minus b of x n. Then if we remember, if we call x equals x, y, z transposed, then if we write that out in component form, we have xn plus 1 equals yn plus 1 equals zn plus 1 equals something else, equals these things. Okay, so that's just rewriting line by line statement of the Jacobi method. But now, what Gauss and Seidel, or they came up this similar sort of time, since they share the name of it, they realized actually in the first line, if we do it line by line at this, when we get to the second line here of evaluating yn plus 1, actually we've already got xn plus 1. On the right hand side we've got x of n. So the Gauss-Seidel method basically said, well, let's replace x of n with xn plus 1 because we know it from the previous step. And then when we get down to the bottom line as well, we've already got xn plus 1 and we've already got yn plus 1. So the hope was that these red terms here, this is the so if we call Gauss-Seidel GS, these are the GS modifications. the hope is that it accelerates the method, it makes it faster. In general, it does. We're going to analyse that. So if we were to write out the Gauss-Seidel method now, we'd have the following. That xn plus 1 equals 17 on 7 plus 2 7 y of n minus 1 over 7 z of n. Yn plus 1 equals minus 13 on 9 plus a ninth x of n plus 1. That's a modified term from Jacobi. Using the, before it was xn, now it's xn plus 1. And a third z of n. Then you have zn plus 1 equals 3 on 2 minus a fifth xn plus 1 tenth yn plus 1. And these are the other, so these are the modified terms again. And when we evaluate, the GS algorithm involves line by line evaluation, like above. Not from the example with the Jacobi. When you see a Jacobi method, you do C minus B times X at each stage. It's not possible with Gauss-Seidel because you need to have it broken down into its components like this, so that you can use the most up-to-date value of X in the previous step. So it's quite a simple modification, but it's a very useful thing for analysis because structurally it's differently from Jacobi, and it can help us understand methods for convergence and so on and so forth. So what I've done so far is introduced the two methods, Jacobi and Gauss-Seidel, two examples of iterative methods of finding the solution to AX equals B. Now we want to start on a journey of analysis of these methods. So, if you like, methods of Jacobi, and it's here where the sort of more applicable things from this module come forth, because the methods we use are not just applicable to Jacobi and Gauss-Seidel, they could be applied to much more sophisticated methods like conjugate gradient methods or what have you. So there's a reason for using these sort of simple Jacobi and Gauss-Seidel methods as illustrative of these different methods. So the key starting point, and keep my eye on the time there. The key starting point is decomposing. We're going to decompose A. And the decomposition is this. L plus U, D plus U. Now, the L and the U here are, so they've got the same symbols as L and U using LU decomposition, and they are almost the same, but unhelpfully there's a subtle difference that I'm going to highlight. So this is a strictly, and I'll explain what I mean by strictly, lower triangular, and this is strictly triangular. And then this D is a diagonal, purely diagonal matrix. So strictly implies, in this instance I'm using strictly, implies has 0 diagonal. And it's this point that it differs from the L and the U used in LU decomposition, yeah? The L and the U used in LU decomposition had a diagonal element. Right? But the L and the U here are strictly lower triangular and strictly upper triangle. They have no diagonal. And the best way to remember it is that we're making A into a summation of 3 matrices. All the diagonal bits go into D. So it makes sense that L and U have no diagonal in this case. Okay, so that's the easy way to set that. So this is another form of decomposition. It's a summation decomposition. And by doing this, it will allow us to quantify how to generate that B matrix, remember in the Jacobi method, automatically. So A equals L plus D plus U will enable us to calculate B in xn plus 1 equals C minus B of x of n Jacobi directly. Sounds Cornwall. It allows us to calculate this rather than the sort of rather cumbersome in the long term method of using all the simultaneous equations. So the simultaneous equations method that we started with, it was a helpful intro into understanding where this B matrix comes from, but there should be a more automatic way, and this decomposition is going to be a helpful way in. So let's just illustrate with a 3x3 matrix example how this decomposition works. In fact, so we're going to do L equals L plus D plus U by that. I'm just going to use the full board actually for this. 7 minus 2, 1, 1, minus 9, 3, 2, 1, 10. That's our original A matrix that we started with when we looked at iterative methods. In fact, I'm going to use more than one line here, I think. And because it's summation, so we have L plus D plus U, all we are is just repartitioning the different bits. So the L bits are just taking off this lower corner, and then the rest is zeros. D bit is just taking out the diagonal, so it's diagonal here. That's, and then zeros everywhere else, and then upper triangular is just that. Okay, so it's just there's no clever, elaborate transformation here. We just partitioned off the different bits of the matrix, the lower triangular bits, the the diagonal bit, and then the upper triangular bit. Okay, and that's it. So what I want to show you then is how we can use that L plus D plus U decomposition to generate the B matrix automatically. So We've got ax equals b, it's the original problem we're solving, but we're now decomposing a into L plus D plus U. And remember, we want to get it in terms of x equals something. So we partition L plus U off into x and then D onto x into B. This implies that D times x equals B minus L plus U of x. Then to get x on the left hand side, we just multiply through by, remember we've got matrices here, we don't divide through by D. Do multiply by the inverse of D. Okay, so that gives us x equals inverse of D times B minus inverse of D times L plus U. And look, it's in the same form. It's x is C minus B of x. Yeah, that's the form that we're looking for. So that implies our C vector is inverse of D times B, and our B matrix is simply inverse of D times L plus U. So whereas before we were just manipulating different simultaneous equations to get the answer, we now have a recipe for getting our B matrix and also a C matrix as well. That if we do this decomposition, we can then split off as we require. Okay. And the next step is to do this with the Gauss-Seidel method, but I think I'm going to leave that till next time. I'll consolidate the two. So let me just go over again what we've done. So we've got ax equals b. We've done this substitution. We just rearranged it so that x equals something, and then we identify that as the B matrix. So we should now have a recipe for reconstituting B should we require. Okay, and I'll leave that till next time.